Okay, so in this question, we've been presented with a situation where a mystery hydrocarbon has been burned in excess oxygen. And we've been told the masses of carbon dioxide produced, water produced, and we've been asked to determine the empirical formula of this given hydrocarbon. Okay, so how are we actually going to work that out? And what are some of the things we can assume based on the question? Okay, so based on the question, this question tells us that the hydrocarbon was burned in excess oxygen. Okay, now the implication if the hydrocarbon was burned in excess oxygen is that this was a complete combustion which took place. And what does that mean? Well, if a complete combustion takes place, effectively the output as far as the all of the carbon which was in the original hydrocarbon, right, will go into forming carbon dioxide, right? And so the carbon in the original will be the same as the moles in the carbon dioxide. That will be a 1-to-1 ratio. And the hydrogen present in the hydrocarbon, that would all go into producing the H2O, right? So, and in terms of the hydrogen from the hydrocarbon and the hydrogen in the H2O, overall, and this is overall, just to be clear, it's not the this is not a molar comparison between the moles of H2O and the moles of hydrogen, but this is to say all of the hydrogen that was present in the original hydrocarbon will now be existing in the products as hydrogen in the in the water molecules effectively. So in terms of the actual hydrogen would be 1-to-1, effectively saying that there's not a separate byproduct which the hydrogen went into. Okay, and so given this, what can we kind of work out? Well, we can then therefore use the masses of these products to work out the moles, and from the moles we can work out and do some calculations to work out the empirical formula. Okay, so we need to use a formula for this, right? So we need to probably refer at this stage, right, to the moles equals the mass divided by the molar mass formula, right? And we don't have the molar masses just yet. I mean, you may be aware of what the molar masses of carbon dioxide and water are, but just for the sake of comprehensiveness and clarity, I will be having a go at working those out. So, okay, so if we take a look, what we're going to find is that effectively, if you got the 12, so we're going to do the carbons first. So 12 is going to be 12. So CO2, right? So 12 multiplied by the occurrence of the carbon, which is 1, plus the occurrence of the oxygen, so O2, so that's going to be plus 16 times 2, and if you work that out, you should get 44. So therefore the MR for CO2 is going to be 44, and if we do for H2O, hydrogen would be occurring twice, so that's 1 from here, 1 times 2, plus the occurrence of oxygen, which is, as you know, would be 16 times 1, since H2O, the O occurs once, and that gives us 18. Okay, so there we've got the MR of H2O is 18. Okay, so we've got the molar masses now of both, right? So we can kind of move on from there. We can use this formula to kind of go through the next stages, right? So in this particular case, what are we going to do? What are we going to need to do? So we've got 382.8 as the mass of carbon dioxide. So here in this case, we're going to do 382.8 divided by 44, right? And so this is on the CO2 side. And on the moles of H2O side of things, we're going to do 62.64. So that's effectively it's the mass of water divided by the mol of water, which, as we worked out, is 18. And so at this stage, I would invite you to have a go, figure out what these are. And yeah, so if you do that, what you should find is that for if you do the 382.8 divided by 44, we should get 8.7. And if we do this 62.64 divided by 18, we should get 3.48. Okay. Now, for the water, we do need to consider the fact that well, the ratio between hydrogen and as I was saying earlier on as well, we know that the hydrogen that was in the hydrocarbon exists in the water, like it all went into producing water. But that is not to say that the ratio of moles of hydrogen atoms and the moles of water molecules is a 1-to-1 ratio, right? So if you do look at the formula, you can kind of see that for every water molecule, you've got 2 moles of hydrogen, right? Right? So therefore, the ratio of hydrogen, right, when we're looking at H compared to H2O, you can see that for every 1 mole of H2O, we're going to have 2 moles of hydrogen. And because of that, when we need to convert this, which is the moles of H2O, back to moles of hydrogen, which is what we need to do at this stage to kind of get towards the empirical formula of the hydrocarbon, that effectively the moles of the hydrogen is going to be actually 3.48 times 2, right? And what does that give you? Well, that gives you 6.96. Okay, so therefore the moles of hydrogen here, we can say that is going to be 6.96. And let's establish a ratio at this stage. So now we're going to say, okay, so the moles of CO2, well, actually, what I'm going to do, because of the stage we're at, we're not going to work with CO2 anymore. What we're going to work with is carbon, right? So, but it is a 1-to-1 ratio, so the number would be the same. But I just for very for precision purposes, we're going to work now with moles of carbon, right? So for moles of carbon, it's going to be the same. As I said, it's a 1-to-1 ratio, because for every CO2, you can see this is like, you can imagine, right? This is for every carbon, you've got 1 mole of carbon dioxide, right? So that's a 1-to-1 ratio. So effectively, that 8.7 is what it's going to be, right? So the ratio here is 8.7 to 6.96. Okay. So at this stage, we're trying to achieve the simplest whole number ratio. So the first thing we're going to do is we're going to divide both sides by the smallest number. Right, so we're going to divide 8.7. We're going to divide that by 6.96. And 6.96, we're going to also divide that by 6.96. Right? Now when we do that, what are we going to get out of it? Right? So obviously when we do this operation here, we're going to just get 1, right? On this side, on the carbon side, when we do that operation, if you have a go at that on your calculator, what you should find you get is 1.25, okay? 1.25. Now we need to kind of work towards getting this to an actual whole number ratio, because at the moment it still is not a whole number ratio. We've got a 0.25 here, which is obviously not a whole number. So what we need to go through now is a process of scaling up effectively, and you can kind of cycle through, like, okay, well, if we multiply it by 2, by 3, by 4, what is the lowest number we can multiply this by for it to become a whole number? Now, for some people, just based on visual inspection, it should be quite clear what that number is that you need to multiply it by to get a whole number. However, just for the sake of comprehensiveness, I will go through the process step by step, just for because with more complicated numbers, you would sometimes have to actually go through this process, and on some occasions, as you might later on see or you might see in other questions, there are cases where the number you're going to come up with at the end is not going to be exactly a whole number, and there's going to be some level of rounding involved to really get to what you know. But in any case, let's work with what's in front of us. So if we multiply this by 2, right, what do we get? Well, if you multiply it by 2, and we're just going to write the product over here, right? So if we multiply it by 2, we're going to get effectively 2.5, right? 2.5 to 2. Is this a whole number ratio? No, it's not. Okay, if we multiply this by 3, what do we get? Well, if we do it by 3, we get 3.75 to 3, right? Because we're multiplying both sides. Is this a whole number ratio now? Well, clearly it's not. Now let's have a go at multiplying it by 5. No, not by 5, by 4. So if we multiply it by 4, effectively we're going to get 5, right? So we're going to get 5, 4. Okay, so what we've established is now when we multiplied both sides by 4, we did actually get a whole number ratio. And is this the simplest whole number ratio? Well, yes, this is the simplest whole number ratio. So because of what we've established here, we know that, okay, what we actually need to do here is multiply both sides by 4, right? So this is what we're going to do, times 4 times 4. And what do we get? We get, as we established, we get 5, 4, right? I remember, so the 5 is relates to the moles of carbon, the 4 relates to the moles of hydrogen. So therefore, when it comes to our empirical formula, we know that effectively it's going to be C5H4. Okay, so that is our empirical formula in this particular case. Okay.